students, to this AP question solution. All right, I'm going to quickly do a recap. So we've got a pebble of mass m over here, and it is loaded into a slingshot and pulled back at constant velocity from 0 all the way to 3D. Now for part A, it asks us to rank the net force on the pebble at locations D, 2D, and 3D as it is being pulled back. Okay, so they're asking for net force. And net force, we represent it as sigma force equals mass times acceleration. All right, so acceleration in this case for at D, 2D, and 3D, what is it? Well, the hint is right here. Constant velocity. If you remember, constant velocity means that acceleration equals 0. So what does that mean? That means the net force equals mass times 0, which just equals 0. So what does that mean? That means that the net force at D equals 0. The net force at 2D equals 0. And the net force at 3D equals 0. Let's now solve part B. Part B says, find the K value of the elastic band in terms of F3, which is the force at 3D, and D. So our answer should only include variables F3 and D, and possibly some other numbers along with it. Okay, so if we look at our original introduction to the problem, it says that it is a massless spring. So what does that mean? That means we can use our spring equation, which is Hooke's law, which is force of a spring equals negative K times X. Now remember, K, what we're trying to solve, that is the spring constant. So if we solve for this really quickly, we get K equals force over X. And this is negative. So what do we need and what do we have? We have the force of the spring. We already know that that is F3. And we just need to know how much the spring is displaced, or how much it is stretched from equilibrium. So you might think, oh, well, that's easy. That's just 3D, right? That's this distance from here to here. It is stretched from 0 to 3D. But that's not quite the answer. X is actually the distance it is stretched from equilibrium. If you notice on our graph over here, you don't really have to apply any force from 0 to D. So that means that the little rubber band, it's got some distance it can go before even being stretched. And that distance is D. So in reality, the elastic is only being stretched from D to 3D. So what is that distance? X is just equal to 3D minus D, which equals 2D. So that is the amount the spring is being, or the elastic is being stretched from equilibrium. Okay, so all we have to do is plug in values, and we get, let's see, we get K equals a negative force of spring all over 2D. And we know force of spring is just F3. Now, let's think about it. F3 is the force that is applied on our little pebble, so that's pointing to the right. Now, the force of the spring is going to be opposite, equal and opposite. And we know that because it is going at constant velocity. We know that these forces are canceling each other out. So our force of the spring is actually going to be equal to a negative F3. And we have to include the negative right here. And so these negatives will cancel out. And that gives us K equals essentially 1/2 F3 all over D. Now let's look at part C. Determine the work done by the person, by the elastic, and the total work. Now, if we want to find work, all we have to do is look at our force versus distance graph. The work done is simply going to be the area underneath our curve. Now this curve here is the force by the person pulling on the pebble. So that's going to be the very first part. So the area of this here is going to be that of a triangle. So our work is going to be equal to 1/2 base times height, because that is the area of a triangle. The base of this triangle is going to be this right here, which is going to be 3D minus D, and that's going to be 2D. That's going to be equal to the base. So that equals 1/2 times 2D. And then the height in this case is going to be our force, which is just F3. So this is just F3. And so our work is equal to just F3 times D. There we go. And now we have to find the work done by the elastic, or the spring. Now we don't really have a nice graph like up here, which is the applied force versus distance, but we can make it up. We have enough information to know what it'll look like. So our applied force graph looks something like this. Now, since we know it's at constant velocity, that means that the forces are always canceling out, whether you're at D, 2D, or 3D, or anywhere in between. So what does that mean? That means that our applied force is always canceling out the elastic force. So they're always equal, but opposite. So force applied is always positive, right? Because it's in this positive quadrant up here. But the elastic force is going to always be negative, but it's going to be equal and opposite. So it's going to look a little bit like this, where all the area is negative. Now the work that we got by the person, we determined was work equals F3 times D. The work done by the elastic, so I'll do WP for that, work elastic equals the negative. It's just going to be equal but opposite, and it's going to be this negative area down here. So it's going to be negative force 3 times D. If we want to find the work total on the object, on the little pebble, we're going to add up these two. And that's going to result us with F3D minus F3D, which is just equal to 0. So the total work done on the pebble is just going to be equal to 0. Look at part D. How many times greater is the elastic potential energy at 3D compared to 2D? Okay, so for this one, we're dealing with elastic potential energy. If we remember from our Hooke's law equations, we know that potential energy of a spring, or elastic system, is equal to 1/2 K, the spring constant, times x squared, where x is the amount it stretched from equilibrium. Now K, we got that value from our previous part, and that's equal to 1/2 times F3 all over D. Okay, so let's look at the case of 3D when it's stretched all the way to its max. What is the potential energy? So U, spring, and I'm going to do a little 3 to signify that it's the case where it's stretched to 3D, is equal to 1/2 times K, which is 1/2 F3 over D, times our x squared. Now, how much is it stretched in this case? Well, if it stretches from D to 3D, that's a total of 2D distance. That's how much it is stretched from equilibrium. So we'll plug that in here. That's 2D, and let's not forget the square. Now if we calculate this out, we get 1/2 times 1/2 F3 over D times this squared, which is going to be equal to 4D squared. Now it's nice because some things will start to cancel out. This 4 cancels out with these 1/2s, and one of these D's cancels out with this D, and we're left with, this is equal to F3 times D. Pretty easy. Okay, now let's look at the case for potential energy of the spring when it's stretched to 2. So we're going to do the same thing. We're going to do 1/2 times let's see, 1/2 F3 over D, that's our K value that we know, times our distance it's being stretched, where in this case it's only going from D to 2D, so that's just going to be a single D that it is being stretched by. So it's going to be D squared. This gives us a value of, let's see, one of these D's cancels out, and we're left with 1/4 F3 times D. And from here, if we look at the difference between these two equations, we notice that US3 is equal to 4 times US2. So it's 4 times as great.